To get started, I'm still working on getting an assignment up. I don't know if it will be up this week, so I'm guessing at this point, what means is that the first assignment will be due a week from next Wednesday and not next Wednesday. So you can anticipate that being the case. I also have noticed a bit of a, I don't necessarily want to call it an issue, but a pacing improvement that we can make in the class. So I'd like to specify that at any point, if I ask a question to the class, I think it would be best for the class health as a whole if people who would like to answer that question raise their hands. And then I can decide on and call on different people. I will not cold call. I never cold call people. Don't worry about that. But I would like to spread around a little bit of the answer, the call and response that happens in the class to make sure that everyone who would like to contribute and get some feedback on their thought process or to do that has the opportunity to do so. All right, any questions before we dive back in? Okay, let's do it. We were in the middle of a third example of converting code into running times. This time we were looking at a version of a basic setup for Go Fish. And to do so, we needed to go through this code process. Let's just zoom in on this for a second. And the process was we're going to make a deck of cards, we're going to shuffle that deck of cards, and then we're going to deal a hand to the player and to the computer off the top of that deck. So the question we had was, what order are all of these calls in, and what order is this Go Fish function in? And how can we figure that out? Have we had a chance to look at this between yesterday and today, or think about it? Anyone have any ideas about how we might analyze, especially the lines in bold that are calls to functions that we don't have access to here? So there and then there potentially.
Well, we talked about deck already.
Yeah.
Because we want to be creating part for every suit and for every brick. And so we figured that is some form of linear, right? Really like 4n or 5n plus something, depending on how many suits there are.
Yeah, we'll call it R times S just because it is linear. If you think of the number of the cards in the deck as n, there are n cards in the deck. But potentially, in the worst case, we could scale those two dimensions separately. We could add additional suits or add additional ranks. So this tells us a little bit more information about exactly how many cards there are in the deck. It's made up of the number of cards that are ranked times the number of suits that exist. Anything to add?
What I had said is, with the version of Shuffle I was imagining,
Yeah.
it would, since we already knew deck is R times S, I was imagining Shuffle as just swapping the position of two cards within the deck.
Okay.
So I imagine it running Shuffle as like R times S and divided by 2.
Okay. So let's think about that process of shuffling, because I think there's a lot of interest in there. So swapping cards for this seems reasonable. You could even decide, as you're using the divided by 2, of kind of which cards go into separate positions. And once you've figured that out, then you don't need to query that spot again. Let's go through this from the bottom and then see how maybe an R times S procedure could be divided by 2. So in a shuffle, we really have a 52 element array of cards that are, I'm assuming it's an array list. It could easily be a linked list, but I think an array list would be faster for this. Anyway, this is not 52 cells. I imagine that I have enough time and energy to draw 52 cells. The first question would be, what card goes in this first position? I'm going to assume that this first position refers to a deck of cards, and this is the card that is on top of that deck of cards. And so we could just rotate this to be the deck of cards that is vertically in front of us visually, but now it's in an array form, top of the deck, bottom of the deck. We want this card to be a random card. How would we make sure that there is an equal chance for every card in this array to end up in this position? Well, we could just use a random number generator between position 0 and position 51 to say that is going to be the card that is on top of the deck. So we could do that, and when we do that, we're going to swap the elements of whichever one we pick. Let's say we pick this position. We could swap what's in the first position with what's in that position, and now we have guaranteed a random card in this position. Do we agree that there's an equal chance of every card, if we choose a random number between 0 and 51, that ends up being the first card in the position? Equal chance?
Yes.
Great. So we're going to now pick a random number between 1 and 51. And that is going to be the card that we swap into the second position. Do we agree that there's an equal chance, 1 in 52, of all cards being in that second position?
Yeah.
It's a little bit harder to see because now we've made a guaranteed decision about what's in the first position. But it is true that there is a 1 in 52 chance that any particular card ends up in the second position, given that you're doing exactly this. The same thing will happen for position 3, position 4, position 5, all the way to the last position. Once you do the second to last position, the last position is guaranteed to be whatever is left over. You don't need to swap it with itself. So that procedure is not quite R times S. It's very close to it. We'll see in a second. How do we get the divided by 2? How could we have the time of this procedure?
By moving the first position card into the card that just went into first position.
Yeah, I think I understand what you're saying. The way to do it is basically to lock the position. And if we're going to swap this position with that position, we lock this position and we lock this position. So we don't ever need to say what card goes in this position ever again, because the card that is in the first position will now have a 1 in 52 chance of ending up in any of the remaining cells. So when we get to this place, it already has a random card in it. We don't need to do it again. That's more complicated than the answer to this is going to assume that we are using. But that would be a way to have the complexity of the procedure. And that is a constant. It won't change the order of the shuffle since we're just dividing it by 2. That's a constant. But anytime you can reduce the complexity of something, it's usually worth doing. All right. Let's look at why this is. So the entire thing is in order R times S, but it's worth looking at each one of these steps and understanding why we get exactly what we have here. Knowing that we're looking at an answer to this, why is the deck R plus 1 times S and not R times S? It could also be R times S plus 1, if that helps. That's actually a user decision. Yeah?
Is it because of like the implementation up inside of the loop? That
Yeah.
everything has to happen naturally.
It's exactly the same thing that we've seen in every other example that we've talked about so far. How we would do the new deck is we would basically, this code would have a nested loop in it that in pseudocode says for each
Yeah.
rank, actually, let's go for each suit. Inside of that, for each rank. And now when we pick a suit, we're going to pick suit 1, and we're going to go through each rank, A, 2, 3, 4, etc. And we're eventually going to fall off the end of that, and we're going to have to check the suit one more time. That would be the R times S plus 1, and if we did for each rank, for each suit, Now we don't have that anymore. Now we would be checking each rank at the end. So we make all of the aces, and then we would be checking, all right, is this suit in position? No, it's not. We fall off the end. And so we have to check the suits 5 times rather than 4 times because it needs to terminate that innermost loop. So that's how we get the +1 on either the R or the S, depending on the order of these nested loops. And you make the deck regardless of which order you do that in, whether the inner loop is the ranks or the suits does not matter, but it changes which one you're checking for the extra time. Does that make sense? Well, any questions on that? Right, everything else I think is fairly straightforward. The shuffle here as RS +1 is the +1 is not hugely relevant here. If you define some other procedure and to justify exactly why that procedure works or doesn't work, you can put anything you need there. But again, we can sum this all together to get a sense of what the running time is. Note that when we have a constant in this loop, even though a loop typically makes you think we're going to run this n times for some n, if the termination condition is a constant, then that loop runs a constant number of times. So that's why we see 7 times or 8 times. Why is this 8 and not 7?
Because it needs to run one more time to check and see if it's hit 7 or not, and then terminate it.
Exactly the same reason. Yeah. So we're going to check, is 7 less than 7 at the end? After checking 0, 1, 2, 3, 4, 5, 6, all those were successful, and 7 is the 8th time. Yeah.
Why does player hand on that deal only one step?
We do it 7 times, but you're dealing, basically the deal function here is going to deal a single card off the top of the deck.
And then adding is also, so we're saying that the operation of adding to the player's hand is and removing from the deck.
Gotcha. You can state it either way, and it would be fine with me. It is technically 2 things. Deck.deal does one thing, and you're going to add it to the player's hand. So you could easily see this as you do 2 steps 7 times, and that would be perfectly justified. But it is still constant, which is what's important. If we add all these things up, we're going to end up with a large constant based on the things that are happening exactly once. Even if we're repeating it a bunch of times, it's still happening a constant number of times. That doesn't scale with the size of the deck. It scales with the size of the player's hand, which is a rule in the game. I still think this is better as a class constant, but the reason that this is done this way is that when you see something that is a constant in the loop, you know that it's not a variable, it is still a constant. So what order is this in? If we were to sum all of these up. What does n mean?
RS.
Yeah,
Yeah.
that's gonna end up being in theta of RS, which however you'd like to define NN, if your n is the number of cards in the deck, then it is theta of n. If it scales in rank and suit, you can see this as n squared, but in this case, n doesn't represent the same thing. So we don't really want to use n because it's not the same variable representing the same idea. So I could see this as theta of n, where n represents the number of cards in a deck, or I can see it as theta of RS. We're scaling multiplicatively based off the ranks and the suits. But I think n squared is a bad choice here for that reason. Whenever you use a variable, it should represent an idea within the scope. Just like a variable represents the same idea within that scope. If I declare a variable called n within a particular scope, I don't want it to mean 2 different things. The size of the ranks and the size of the suits. Not the same idea, it should have the same name. Yeah.
How would it change if like the hand size wasn't hard coded?
Yeah, that is a good idea. So it should scale based on the hand size. So here we would have a hand size. So we would have something like theta of RS plus H. And there'd be a constant in front of this H being the number of times that we that we do 1, 2, 3, 4, we do 4 times the hand size number of things, but it happens after this. It's sequential. Whenever we see lines like this that are sequential, we add them in complexity because they're happening one followed by the other. That takes time additional. So let's say I ask you to go home and do the laundry, and once you're done with the laundry, then clean out your car. How long does it take to do those? It's the time of one plus the time of the other because they're happening sequentially. On the other hand, if they're embedded, if one is inside of the other, we have a for loop inside of a for loop that says for every step of your laundry, clean out your car. Or clean out somebody else's car. So you're repeating that process that many times. That's why nested loops are multiplicative and sequential loops are additive. Yeah.
So when it comes to like this skill that we're gonna apply to the test in here, are we looking to be able to precisely how many steps? Are we just trying to create this RS plus H, or are we just trying to look at this and see, yeah, it's linear because we're working out from some end?
That is a great question. From my perspective, these are the steps to build the understanding to be able to produce this. So the end goal, what I'm going to be most interested in people being able to divulge moving forward, is finding the order. And not necessarily looking at every single line and analyzing the exact complexity of every line. But I do need to motivate how we come up with this by a line by line analysis of code. So I certainly want to start here, but I am more interested in this than I am in this.
I'm a little confused by if you have 2 variables multiplied together, is that the same order as if you have 1 variable?
It is not typical. So yeah, if you multiply 2 things together, it's going to scale differently as the size of the task grows. So think of laundry being a 10-step process. I don't know if laundry is technically a 10-step process, depending on how we break it down, but let's assume we turn this into a 10-step process. If we're, for every step of laundry, doing an entire laundry cycle, that's how that would become quadratic. Then how does this scale as the 10-step process becomes an 11-step process, as the 11-step process becomes a 100-step process? If we were just looking at laundry as a one-dimensional object, one way we can think of this is kind of to draw it out as an array. Here's the one-dimensional project, and here is the 2-dimensional project. So we can see that it's in a different order because as we add a unit to the end of the one-dimensional task, we are adding a significant amount to the 2-dimensional task. It's not proportional. If we looked at this area divided by this area, that would change as this grows versus this area and that area. If we looked at the ratio of, let's look at that divided by that versus this divided by that. That ratio changes as this scales and becomes a larger and larger piece of information. That's how we know it's in a separate order. It doesn't scale consistently. It doesn't have the same ratio. The ratio grows as the input size scales. Yeah.
So then, I guess, I understand that if it's 2 different variables, that it makes that separate, but in terms of the order, it's the same amount of complexity as n squared. That's
Gotcha. It depends. So if you say R times S, it instantiates them as what the reason that they are growing is the rank times the suit. Whereas if I say n squared, then it's growing in a square necessarily. So it would still reasonably be the same order, but where did my rank go?
That's fine, you.
Literally right behind me. Excellent. Like peripheral vision, it's about that way. This comes down to something that's in practice more so than in theory. I would agree that the idea of it growing at a quadratic rate is something that is consistent. But if we have in some case something that is very rectangular, like there are more ranks than there are suits. As we scale a rank, we are adding a smaller piece of information. As we scale a suit, we are adding a larger piece of information or data. So if you break it down into those two components, if it's something that is in practice, we get a sense of how much more are we adding by a constant factor here than here. And in theory, the constant factor doesn't matter, but in practice, oftentimes that constant factor does matter. So if you're looking at the theoretical order, it's worth saying these are two variables because those variables may scale very differently and have different reasons to scale differently in practice. It may be that in the game of Go Fish, it makes more sense to add a bunch of ranks than it does to add another suit. If you were coming up with a new version of Go Fish with a new kind of card deck. And then in that case, seeing it as n squared, it would look like it's exactly the same to add a rank as it is a suit, when in practice, that would have a slightly different computational effect on the complexity of your project. Yeah.
So I have a question, because we aren't changing size of the deck within the Go Fish method and the shuffle, how come we don't simplify each of those down to one step each and then call this a constant runtime?
Interesting.
Because if you call Go Fish, it's always gonna run the same.
It will always run the same, but the amount that it runs does scale with proportion to the deck size. Since the deck is constant, we would want to call it constant in that regard because the deck is consistent in size, but it is technically a variable that could scale. It is something that the complexity of it is with respect to the deck size. So because of that, we utilize a separate variable for that. But that is a great question. Yeah.
Kind of in the same theme as that question, if we're saying that the deck could be different sizes, then why are we saying that it's only two variables, the rank and two? Can we add in a third? There's pictures on the cards.
we could. Yeah, we could add a third dimension to that, a fourth dimension to that. At some point, we have to decide what are the variables that could scale and which are the variables that could not scale. And we have to base our analysis on those assumptions. Those assumptions are embedded in the logic that we are doing. But yeah, it could be that later on, this project scales in size, which means that we have to go back and reanalyze some of the assumptions that we've made and incorporate new assumptions into our logic. That's fair. This is not a class that's going to have frequent right answers and only those right answers. If you ever on an exam or an assignment do something and then justify what you've done, I will frequently take that at face value, look at your justification and say, that makes sense given your interpretation of the problem. That's not wrong. That is an understanding of the problem. So I will not mark you down for something like that. Computer science is a field of knowing what you are doing and not answering exactly what I am expecting.
Good to know.
I tend to be flexible. You do have to justify it, and that justification has to make sense. You have to have thoroughly walked me through your thought process, and I cannot be able to poke a hole in your thought process. But you walk me through your thought process, and that process is right, and it answers the question, and it's not what I was expecting. That's great. All right, last one.
Oh, okay. Well, it's got a double sum. I'm taking a double matrix. Oh yeah, double. Wait a second. That's a two-dimensional matrix.
It is a two-dimensional matrix array.
I haven't seen one of those in a long time.
Take a few minutes, let's talk to each other, and let's see if we can come up with a running time for this.
Well, it is a mystic. Well, at least we have some good ideas on where to start. The current and next is for people stuff. One minute, it's going about. N times. One times. Right. One, okay. Well, what is that? Let me think. Too much M times C. Like. Oh. Hold on. Different ones. I will. One percent. We're speaking stuff. Saying this. Wait, one thing I forgot actually. It's kind of like, oh, yeah, I forgot that. It's like.
How are we doing? Do we think we have an answer? Reasonably?
Something close.
Let's talk about it. So I'm actually going to disagree with the book a little bit here. This is the exact thing we were just talking about with regards to.
Oh, what's what the one part with the matrix that or the double matrix?
It is being called, it's being passed in once. That matrix is not being created here, it is being passed in.
Good to know. Wow.
So it's being passed in as a reference, so that reference variable is being assigned once.
Also gonna have to admit, to be honest, I did not use the same variable as the book did here.
That is fair. I also would not. That is exactly what I'm about to criticize. Because we don't know if this is a square matrix or if this is a highly rectangular matrix where the number of rows and number of columns vary. And it's worth breaking that out to me and seeing how this is based on the rows and columns of this matrix.
It might be two-dimensional, but it's not always the same.
Yeah, so this should technically, instead of n, from my perspective, be an r. We're gonna be running the inner loop and checking it a bunch of times, which means that this n is our C, this n is our R. And then this should be R and C. And
Oh,
yeah,
What are R and C standing for here?
the number of rows and number of columns in this matrix,
X and Y.
X and Y works as well. As long as you have two separate variables that represent the number of rows and the number of columns, I would agree that that is technically better because it looks at the multiplication of rows and columns, and we can see a big difference when we have the same number of the sum of something. Like let's say we have R plus C is 100. What are the most extreme cases we can make for this? We can make R equal to 1 and C equal to 99. Or we can make R equal to 50 and C equal to 50. What is 1 times 99? This would be 99 steps. What is 50 times 50? 2,500. There's a reasonable difference here between an R and a C. If we say n times n, these are the largest possible extreme of a difference of the amount of work that we're asking based on whether we choose something that is extremely rectangular versus something that is square. If you're going to multiply two numbers together and you have a limit on the size of the sum of them, the best thing you can do is make them equal to each other or as close to equal as you can, and that creates the largest area you can get. So this ratio is 25 times as much work here as there is here. And that's worth, in practice, even a constant factor of 25 can be a meaningful factor. So it's at least worth considering. The only thing we've done is change the variables. None of the other work has changed. It all stays the same, but embedded in R and C is potentially this kind of difference. And this ratio scales the larger these numbers get. So I said this sums up to 100. If we sum up to 1,000, we end up with 999, which is just basically 10 times that size. 500 times 500, we're adding 2 more zeros to the end of this. So this ratio grows as we allow for larger and larger things. So because that ratio grows, that's embedded in the R times C, and that ratio is not embedded if we're using the same variable. So again, to me, that's why it's better to use 2 variables than 1. Questions about that? I would still call this quadratic. This is not linear with proportion to R and C. This is quadratic. Because we have 2 variables that will scale together. Other questions before we move on? How are we doing so far? I tend to, those of you who've had me in classes before, I like to use a show of thumbs to show kind of a general level of understanding and comfort and confidence in a topic before I move on. How do we feel about this kind of work? Do we feel confident? I could do this all day, every day. I would like more practice with this, but I get the general, I think I get the general idea, but there are some places where I could use some more work. What's going on? Help.
still could use more practice, but it's going good.
That's what it looks like for the most part, is we're at a place where we understand the basics, but we would like some extra practice with work like this. That means I should throw some practice problems like this on the homework. Good to know. I will do that in preparation for what kinds of questions I would choose to ask on an exam. All right. Next topic we're going to go into, if I can actually erase my entire board. Is a basic overview of when we care about when our running times can scale, or we just have an estimate for a running time. So First question I like to ask people when I do this is, are you more of an optimist or a pessimist? If you feel like you're on the optimist side of 50%, raise your hand. If you're on the pessimist side of 50%, raise your hand. It seems like we actually have quite a few people who either were right on 50% or not answering, but we have more pessimists than we have optimists. Good. Computer scientists should be pessimists, and the reason they should be pessimists is it leaves you, you're never upset. But if an algorithm can perform differently, if you look at it from a pessimistic perspective, could this be worse than that? I'm going to figure out the worst that it could possibly be. Then you're never going to be disappointed or surprised. And if you're writing something on a specification sheet about how this algorithm is going to perform, you would rather disseminate information that can't be, where the actual performance of it can't be worse than that. If you are an optimist, then you say, well, if everything lines up perfectly, then this algorithm runs in this order. An example of this is, let's look at insertion sort when the list is already sorted. What is the running time of insertion sort when the list is already sorted? Haven't heard it yet? Yeah. Linear. Why is it linear? Well, let's verify that it's in order. So we're going to check, is the first element smaller than the second element? Yes, move on. Is the second element smaller than the third element? Yes, move on. So the verification process takes a linear proportion of time to the length of the list. Is that a good assumption to make? I've written insertion sort, and when I advertise insertion sort, I'm going to say it runs in linear time.
I think it is a good thing, but I'm not sure how right I am.
It's only going to run in linear time if the list is already sorted. If I feed it a list that's not sorted, the person who's running this says, I expected this to take linear time. Why is it taking longer time than you advertised? You say, well, I only figured out the best case. And so that's what I used to advertise how long this algorithm takes to run. And in practice, that will be different. So we need different ways of communicating how long an algorithm takes to run based on the assumptions that we are making. Are we making a best case assumption? Are we making a worst case assumption? Are we calculating an average case assumption to disseminate? Those are the three main kinds of analysis that we will use when relaying an algorithm's running time. Given that the underlying data representation may be different, the algorithm may run in a different order. So the insertion sort is an example of that. If we're sorting the list, if the list is either already sorted and we're running insertion sort, we get a different order than if the list is not already sorted, or it's sorted in reverse order, creating the most possible work. So we could analyze the running time in very different ways. How does it perform under the best case scenario? How does it perform under the worst case scenario? And how does it perform on average, on an average data set? If we looked at every permutation of data that could possibly be passed, how would it perform on average? So any benefits or detriments to using any of these kinds of analysis? When would you think that best case, average case, or worst case would be useful to disseminate? I kind of already did best case. It's very infrequently useful. Sorry to those of you who are optimists. Never change. Don't let computer science drag you down. When would you want to use something that is worst case?
Stress testing?
Nah,
Stress testing?
right idea, I think, but maybe not.
It's best to figure out how something would perform under load or under the worst case scenario. If you're testing something like server configurations and you would want to figure out what is the worst case of how many players my server can hold before it crashes. You're not going to look at the average number. How does it perform when the average number of players are on the server? That is important, but the worst case is how does it perform when it's about to crash? How would you notice that? How would you analyze that?
Yeah, what happened when you got almost the maximum amount of people
Where is that limit?
yeah, where is that?
So you could use some kind of worst case analysis on that. And in computer science, we don't care so much what happens when things are working nicely. We care about when are things going to break? How long could this take? When can I guarantee you an answer? I can use worst case analysis when I tell you when I'm going to give you back an exam. Worst case, I'll have it back to you by the end of the quarter. Probably want better than that. But if I tell you best case, I'll have it back to you by tomorrow. That tells you no information whatsoever. If nothing else gets on my plate today, which never happens, if no one comes to see me in office hours and no one bugs me and everything that's already on my plate magically gets taken off my plate by somebody else, which could happen, I could have them back by tomorrow. Doesn't tell you anything useful. Similarly, worst case gives you a deadline. It's like you will have this back by the end of the quarter. Also not necessarily useful, but at least it's more useful than the best case. There's a deadline where I know I can, if I don't have it back by then, something happened. Yeah.
Wondering, an example of when best case might be useful, possibly when you're setting like a free version of something. You can stay within these limits because this is our best case.
Yeah.
You can do it for free then.
Yeah, there are absolutely ways and reasons to use best case analysis, for sure. It's just the least frequently used of these three. There will be times, though, where you want to say, optimistically, under these conditions, if we can guarantee these conditions, then this algorithm will perform at this level. So how can we work at guaranteeing these conditions where every list that is passed to insertion sort is already sorted, and we're just validating that it's already sorted, rather than trying to sort it, because insertion sort validates that something is sorted faster than selection sort does. What about average case? Average case seems to be the most useful of the three. It tells you what to expect on average. Why is this possibly less frequently used than worst case analysis?
Got the worst case covered and probably have the best average case covered.
Maybe. The average case, yeah.
Well, I was thinking, I'm not sure if this answers your question, but I was thinking about the BOGO sort.
Yeah.
Because we usually think of BOGO sort in like the worst case, but it is kind of like random, right?
Yeah.
So there is at least an average that will get, it's like more likely to happen than the worst case, right?
Yeah, it's about factorial over 2. It's a constant. The best case, though, is that it happens on the first try. Is that useful? Look at that. We can sort in constant time. We can sort in, okay, it'd be linear time to validate it still, but try it once. Hey, it happened on it. It's sorted. Yay. Let's use it. Let's not use it. Average case is frequently very difficult and mathematical to calculate, and you may not have all of the information that you have that you need to calculate that average case. You may need to simulate a bunch of times, and if you're dealing with something that scales in size, you may need a sample size that is large enough that it takes longer to even get an estimate of the average case analysis than you want to spend on your analysis. In which case, best case and worst case are usually much easier to calculate. And so you can say, well, it won't take longer than this. So it doesn't matter where the average case is in this, the worst case is good enough. Analysis done. Okay. None of this is terribly important now. Yes.
Just a question about average case. If you're comparing two algorithms and you know that algorithm A performs better at the worst case, but algorithm B actually performs better at the average case, then how do you decide which do you want to use it in?
That is a great question. It's going to be very context dependent on whether you care about the average case or whether you care about the worst case. If you're looking at something where maybe you're in a company and they're looking at reviews, who reviews your company? Those who have poor experiences. You might want to prioritize something with a better worst case and a worse average case because you're going to get fewer bad reviews from the people who experience the worst case behavior. Whereas if this is something where we care about the cumulative, how much time does it take in general to do it, and everything involved, you may care to prioritize the average case, but yeah, it would be completely dependent on what you're doing. You should know how to do both and analyze both so that when you're in the appropriate situation, you can make that decision. A lot of the times I will give wishy-washy answers like that because in computer science, there's very rarely a right answer. There's going to be, here are the tools so that you can make an informed decision in the context that you find yourself in. And that answer will change depending on that context. All right, so we'll give you an example. Let's look at array list contains method. Here is an array list contains method. What is our best case scenario? What is true about the underlying data representation in this list if this contains method runs as quickly as possible? There we go.
It's in the first, it's in the
First position, the target exists at position 0 in the list. How long does it take in order to return true if that's the case? What order would this be running in if the target is in the very first position? Constant time. Doesn't matter how long the list is. We're always doing exactly the same amount of work to return, yes, the target was at the first position. How about the worst case? What is true about the underlying representation of the data if we are in the worst case? Either it's not in the list, or it's at the very last position to be the same amount of work for the most part, within plus or minus 1 of each other, yeah. How does that scale asymptotically with the size of the list? Linearly? Absolutely. We have to go through every element of the list. Is it here? Is it here? Is it here? Is it here? And that will scale linearly with the in one dimension with respect to the size of the list. Absolutely. Now we see how it's a little bit harder to see this on average. On average, how long can we expect this algorithm to take? It's still relatively easy compared to questions that I could ask you about average cases, but it's not quite as straightforward as it's in the first place or it's in the last place. Is the average case that it's in the middle position? Maybe. It depends on how likely the target is to be the query. Is this list sorted by how likely it is that the target is up front or in the back? If we are looking at, maybe this is a list of library books, if we sort them by how frequently they are checked out, then the list is, the target is more likely to be in the front than it is in the back, in which case the average case might not just be the middle position. Yeah.
In a lot of scenarios, I feel like it's reasonable to assume that at least half the time it's not going to be in the list.
Yeah, that's true too. How frequently is the target not in the list? So the average case is going to be context dependent on a lot of information that we don't have. And we could use some basic analysis to say, all right, we're going to make the assumption that every element in this list is equally likely to be the target. And 20% of the time, the target is not in the list. Because when you come up with that, you can come up with a function that tells you about how long this should take. But you're making assumptions. How realistic are your assumptions? We didn't have to do any of that for our best case or worst case analysis. It was straightforward. So average case tells you very important information, but it might not be more important than the worst case. If the worst case behavior is good enough, if linear is a good enough time frame, then why bother going through the average case? Because it may end up being linear in the average case. It may end up being logarithmic or constant in the average case. But if the worst case behavior is good enough, why torture yourself? Sometimes that is relevant and useful, and you need to be able to think through the average case. So you should know how to do that, but you should also know what variables to take into consideration. So one thing to note is that the average case is more frequently similar to the worst case than the best case. So this is another reason why we say that the worst case is more important than the best case. if you are analyzing the harder to ask question of the average case, looking at the worst case is more likely to be a better representation of the average case than the best cases. We'll pick this back up tomorrow.
When you were, as we brought up, that works in average. Case scenario, it reminded me of,